Yes. Huh? I need the answer. I need the answer. I need the answers. I need the answers. Provide me the answers, guys. I need the answer to those two problems. Huh? Write it down first. Write it down. Write it down. And if you want to have more fun, you can also do the mechanism for that. Yeah, if you want to have more fun, perform the mechanism. Because remember, I told you guys to do the mechanism 5 times every day before you sleep. And I know why I'm saying so. Told you to do the mechanism 5 times every day before you sleep. You know what? I will change this one. The second one. Yeah. Yeah, you see, everybody is in class. Yeah, of course. I have very few people for work. That's how I take attendance. Yeah. They couldn't pick their paper and not in class. That is easy. Yeah. Yes, sir. No problem. It doesn't change anything. It will not change what I want you guys to learn. Yeah. It won't change the purpose of learning. So, let's do number 1. I will delete number 2, then I will put it back again up, and then we'll look at it. Okay. So let's look number 1. We have 2 sp2 carbon. We have to follow the mechanical rules, and I emphasize that. Let me delete this one for now. We'll talk about that one. Let's talk about the first one. Remember, I said it will be interesting if you do the mechanism of this reaction. Does that make sense? I know most of you will probably give me this as an answer. Okay? This one plus maybe this one. Okay? This first is completely wrong. Why? Okay. So we have the 2 sp2 carbons over here. We have the 2 sp2 carbons. So we are adding on the sp2 carbon. One of them will have the hydrogen, the other one will take the bromine. But based on what we said, because this is a primary and that is a secondary, the primary usually doesn't form. So that's why we will have no primary here. But the secondary, we know that the secondary actually does form. Okay, so most of you, that's the product you will give me. But if we look at the mechanism, if we look at the detailed mechanism, that's what I asked you guys to do. The mechanism for this reaction. What's the first step for the mechanism? Formation of the carbocation. Okay? Formation of the carbocation is the first step of the mechanism. So the electrons leave from the double bond to the hydrogen, and this one breaks to the bromine. So once you do that, you will have this carbocation. That's a secondary carbocation. That's a secondary carbocation. Now this is where everything happens. This is where magic happens. You have that secondary carbocation plus Br minus, okay? Plus a Br minus. This is where magic happens. Don't forget that we have a certain hydrogen here. There's a hidden hydrogen. Now, can you guys see that one? Let me change that ink size. There's a hidden hydrogen there. Okay. Now, because this carbocation is adjacent to a tertiary carbon, does that make sense? Because the carbocation is adjacent to the tertiary carbon, the hydrogen will migrate. So there will be a migration of this hydrogen to this position. Does that make sense? That's an additional step from what we haven't seen yet. There will be a migration of that hydrogen to that position, and it will lead to the generation of a new type of carbocation. The carbocation that will be formed will be this one now. So do you understand why the migration takes place? If you look at these two carbocations, when you compare these two carbocations, do you understand why there's a migration? No, look at it very well. Look at it very well, and then make use of everything we've done. Let me call this 1 and call this one 2. Look at the carbocation 1 and 2, and tell me if you understand why there is a migration. Yes, bro. Yeah, let's. Hallelujah. Praise the Lord, right? So if you look at carbocation 1, it is adjacent to a tertiary center. That's what I first said. And because it's adjacent to a tertiary center, there is a migration. The hydrogen goes and takes the place of the positive charge, and the positive charge takes the place of the hydrogen. Then that creates carbocation 2, which is a tertiary carbocation. Do you see that? So the migration is because we want to form a more stable carbocation. That's why there's migration. Yes.
Does this happen every time?
Every time you form a carbocation that is next to a tertiary center. Every time you form a carbocation that is next to a tertiary center, there will be a migration. Does that make sense? And this kind of migration is called 1,2 hydride shift. Does that make sense?
Okay, but how do you show that?
Just like the arrow, you see that green arrow? You see my green arrow? So I show that the electrons that form this hydrogen will move and get there and come over here. And at the same time, now the positive charge should be over there. So this is called a 1,2 hydride shift. And that is possible when your carbocation is next to a tertiary center, adjacent to a tertiary center. Does that make sense? And that only happens because it knows that I will form a more stable intermediate. That's why it does the migration. Okay? And so your ability to see that is important, because most of the time this is what you'll be given, and so you should be able to know that if I do the mechanism, I will be able to see that migration. Yes?
Do we have to wait for the secondary center?
Well, if it is next to a secondary center and it is a secondary carbocation, there's no point. Does that make sense? If the carbocation is next to a secondary center, then there is no point for migration. You are already secondary, why should you migrate to become secondary again? You know, there's no point, right? Yeah. Does that make sense? Now, that said, I want you guys to look at the second one I gave you, the second problem I gave you. That second problem, the people, well, those who came late, you still have an opportunity here. Those who came late, you still have an opportunity. That's the second problem. After doing the first one, I want you guys to do this one. Tell me what the answer will be now with confidence. I want you guys to tell me what the answer to this one will be with confidence. Do you have the answer? No, not yet. So with this one, H2O and HSO4, what are you adding to the double bond? Hey, first thing, what are you adding to the double bond? H2SO4. No. This is the attendance.
Oh.
Yeah, the problem is above. Attendance is for those who came late to be able to catch up. H2SO4. You are adding water, right?
Yeah.
So one of the carbon will get the OH and the other one will have the hydrogen. Does that make sense? That's what H2SO4 does. Addition of water. And this is an acid catalyzed addition of water. Acid catalyzed. Do we have the answer?
Yeah.
Perfect. Let's see. Now, do you have this as your answer? Do you have this structure as your answer? Silence means no, right? So let's do the mechanism. Let's do the mechanism and understand why we have that as an answer. Say that again? HBr. Yeah, well, that's fine. If you did that with HBr, then Br should be here and H should be there. Okay, those who did that with HBr, replace the OH by that. So that will still be the case. So let's try to understand why the answer is what it is. I will delete this thing here. Okay, so this is a problem. And we are reacting it with our acids. That's the acids, okay? First step is formation of the carbocation. So this goes there and that goes there. So when you have that, you now generate this. That's the carbocation. I will stop there. I will stop at the level of the carbocation. And you can see that's a secondary carbocation next to what kind of center is this? Next to quaternary center. So it's a similar stuff we did. Last time we said a carbocation next to a tertiary center. What happens is a hydride shift. But here now, because we have a carbocation next to a quaternary center, the same thing, similar stuff will happen. Instead of a hydride shift, it will be a methyl shift. Does that make sense? There will be a methyl shift, and the reason is the same. If you now perform the methyl shift, you will now have this. Do you see why we perform a methyl shift? We're doing a methyl shift because we're forming a more stable carbocation. We're forming now a tertiary carbocation. Huh? How do I know? Yeah, you could now. Yeah, now I have informed you guys. Okay. Yes. So this is called a 1,2 methyl shift. The first one was a 1,2 hydra shift. The second one is a 1,2 methyl shift. Yes. You can only move a methyl or a hydride. Okay. You can only move a methyl or a hydride. You move the methyl when your carbocation is next to a quaternary center. You move the hydride when the carbocation is next to a tertiary center. Does that make sense? Are we good, guys? Life is good.
Wait, can you go back? I guess.
So we can continue our business.
Then how does it wind up being the OH and
Say that again.
how does it wind up being the OH and
No, if you follow the mechanism which we did last class, if you continue the mechanism from there, which I will not, because I expect you guys to be able to continue it. I have a lot of empty slides that will be. Say that again. Okay. So you asked the question, the mechanism for the acid catalyze. That's it. We did that last class. Okay, so you can. So start from here. The major product is a surprise. So we've done that already. Now you understand why this is the major product. That's exactly the problem we just did. Okay, so I will skip that so that you guys can go back and do it. This is exactly the problem we did. Okay, exactly the same thing. Same thing with this one. This is a problem we just did together. This would be the major product. But in this case, they were adding HCl. In our own case, we added water. Okay? Same thing, same explanation. If you want to study the mechanism of the hydride shift in detail, you will have it here. That's the mechanism. And over here, you can see the hydride moving, called the 1,2 hydride shift. It moves to create a tertiary carbocation that will lead to the formation of the product. And this will lead to the formation of a minor product because the hydride stays the same. Okay, secondary versus tertiary. We've talked about that already. So that can only happen if your carbocation is next to a tertiary center. Same thing with the methyl shift. 1,2 methyl shift can only happen if the hydride is next to a quaternary center. Hallelujah. Zaria, the carbocation does not rearrange if it is next to a secondary center. You form your carbocation over here. Adjacent to it is a secondary carbon and a primary carbon, so it doesn't rearrange. It can only rearrange if it is next to a tertiary or a quaternary. Does that make sense? And here it doesn't rearrange because there is no point in rearranging. You are secondary, why should you become secondary again? There's no point. Does that make sense? So, done. Now, hydroboration. Hydroboration. Borane, BH3, is an electrophile because it's a Lewis acid. All Lewis acids are electrophile, okay? And it's an electrophile because it has an incomplete octet. And so it needs electrons to complete its octet. And so because an electrophile, it will also undergo the same type of reaction that all electrophiles undergo. Does that make sense? So it can react with a double bond. And so if we have a borane, and then we react that with a carbon-carbon double bond, with the example shown over here, that will lead to the addition of hydrogen and water molecule. So all I need from you guys here is, let me do it this way. This is too big. This kind of reaction is called hydroboration. Okay? Hydroboration. All I need from you guys is to understand that hydroboration leads to the addition of an OH and an H onto the double bond. So it also leads to the formation of an alcohol. So this is a second mechanism, or this is a second type of reaction we're seeing in this class that leads to the formation of an alcohol. The first one is if you react water and an acid, that will lead to the formation of the alcohol. The second one, if you react it with hydroboration reagent, These are the reagents for hydroboration. So you have borane, the BH3. CHF is a solvent. Tetrahydrofuran, that's just a solvent, nothing else. The OH minus is your nucleophile. That adds up, okay? And peroxide and water are just the appropriate reaction condition for things to take place. So what I need you guys to remember here is that hydroboration adds a hydrogen and an OH onto the double bond. But then I want you guys to look at it carefully. The addition of the OH and the H, or let me say the addition of the water molecule onto the double bond, is a little bit different from the acid catalyzed reaction. It's a little bit different, and I want you guys to be able to observe that difference. In the acid catalyzed reaction, if I gave you this, I will say react it with water and acid, the product would be this. Do you see the difference in product? One gives me the secondary alcohol, the other one gives me the primary alcohol. I want you guys to see the difference. Okay. First one here, addition of acid. We said it follows the Markovnikov's rule. You remember the Markovnikov's rule? To those who have more shall be given. So you look at the 2sp2 carbon. The sp2 carbon with more hydrogen will end up with more hydrogen, and the other one will end up with whatever group you are adding. That's the Markovnikov's rule. Yes. To those who have more shall be given. So if you look at the 2sp2 carbons that are forming the double bond, the carbon atom with more hydrogen ends up with more hydrogen. Does that make sense? So these are my 2sp2. This carbon atom has 2 hydrogen, this one 1. And so at the end of the reaction, this ends up with an extra hydrogen. So you actually have a total of 3 hydrogens here. So that ends up with an extra hydrogen, and the other carbon ends up with the OH. That is the Markovnikov rule. But hydroboration follows the anti-Markovnikov rule. Does that make sense? It follows the anti-Markovnikov rule. And so the hydrogen will add to the carbon with fewer hydrogen. Does that make sense? That's the difference between those two reactions. Similarity, they all add up a water molecule to the double bond. The difference, one follows the Markovnikov, the other one follows the anti-Markovnikov. Are we good with that? And that's all I need you guys to know for hydroboration. Yes.
Are there any other exceptions where the anti-Markovnikov will be applied?
We'll look at them, yes. There are other. We'll talk about that. Yes.
So the number identifies how many hydrogen?
Which number?
So you gave it a 1 and a 2.
This 1 and 2 here?
No.
This one here? Oh, this 1 and 2? Yeah, that indicates the number of hydrogen connected to each of the carbons. Okay. So are we good up to this point? So far we've learned 3 types of reaction. Addition, let's do a recall. We've done 3 types of reaction in this class. So we've done addition of HX, where X could be bromine, chlorine, or iodine. We call that halogenation. Does that make sense? Now, we've also done addition of a water molecule. And the addition of water molecule, we've looked at 2 ways of doing that. Acid catalyzed, which follows the Markovnikov rule, and hydroboration, that follows the anti-Markovnikov rule. Does that make sense? I don't want you guys to know the mechanism for hydroboration. Okay? So we'll not talk much about that. And so this is exactly what I was saying here. With the acid catalyzed, you follow the Markovnikov rule. With the hydroboration, you have the anti-Markovnikov rule. Is that okay? Acid catalyzed, Markovnikov, boration, anti-Markovnikov. Like I said, the mechanism, I don't want you guys to worry about the mechanism of hydroboration. So don't worry about the mechanism of hydroboration. Don't worry about that. Now, another thing I want you guys to take note In the acid catalyzed reaction, we had a possibility of carbocation rearrangement. You remember that, right? Hydral shift, 1,2 hydral shift, 1,3 hydral shift. In hydroboration, rearrangement does not take place. Is that okay? There's no rearrangement. So if we react this guy here, these are the 2 carbons of interest. Those are the 2 carbons of interest. So we know it is an anti-Marconi-Core. So there is no rearrangement. That's where our product is. So that's the OH, and the extra hydrogen is over there. There is no rearrangement here. Same thing with quaternary center. These are the 2 carbons of interest. You perform a hydroboration. The OH ends up there, and the H is somewhere there. No rearrangement. That's what I want you guys to take note, because the mechanism doesn't go through a carbocation. It goes through something else, but not a carbocation. That's why we didn't want to worry much. So all I want you guys to remember here is that no rearrangement, and it follows anti-Marconi-Core. Does that make sense, guys? The mechanism is for those who will do chemistry 407 with me. Yeah, next year. We'll do that mechanism together and enjoy it. The 4th type of reaction, reaction number 4. Reaction number 4, addition of Br2 and Cl2. Okay? Addition of Br2 and Cl2. And so if we have our double bond and we decide to add a Br2, a bromine molecule there, this is fairly straightforward. The bromine, each bromine atom will add up onto the sp2 carbon. So these are the 2 sp2 carbon of interest. Then I react with Br2. Each of them ends up having the Br. Does that make sense? They end up with the Br. And this is called a vicinal bromination or vicinal halogenation. Vicinal simply means that adding on to adjacent carbon. So one adds here, the other one adds there. Very easy. The same thing is true with chlorine. So if you do that with chlorine, you end up having a vicinal dichloride. Okay? This is a solvent. That is a solvent. That we call that methylene chloride. So that's methylene chloride. It's just a solvent to make the reaction, make things dissolve and the reaction to move faster or better. Does that make sense with this one? And this one, I want you guys to learn the mechanism, which is a little bit different from what we've done. Okay? So in this bromination reaction, you form an intermediate, which is very interesting. That intermediate is a 3-member ring. And the intermediate is called a bromonium ion if you're using bromine. Or the intermediate can also be called a chloronium ion if you are using chlorine. Does that make sense? So in general, we'll refer to the intermediate as halonium. You can use the word meaning halogens. You remember bromine, chlorines are all halogens, right? So we can call that the halonium ion, or you can call that the bromonium ion if it is bromine, or you can call it the chloronium ion if it is chlorine. It is a 3-membered intermediate. It is a 3-member intermediate. First step of the reaction, there is an attack of the double bond onto the bromine, and one of the lone pairs of electrons of bromine also attack the second carbon. That's what leads to the formation of that 3-member ring, while eliminating the second bromine atom. Once we have our 3-member ring, then the bromine atom that was initially eliminated can easily add up to the double bond. And that's how you end up having your vicinal bromination. Does that make sense? Question? Yes. Always. 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 That mechanism, I want you guys to know it. Question. Yes. Yes, the double bond attacks the bromine first. Then the lone pair of electrons from the bromine attacks the second carbon while releasing the second bromine atom. Okay, that's how you form your chloronium ion. Please correct this. This is a mistake. So this is a little bit of electrostatic potential. This is just a fancy way of representing the bromonium ion, okay? Remember that in this diagram, the red region represents electron rich and the blue zone represents electron deficient. And so in this molecule, the carbon atom to which the bromine are connected are the most electrophilic. So those are the ones with the blue region. And so if you have any nucleophile, the nucleophile will easily attack those carbon, okay, and open up the ring, which is the second step of that mechanism. So the nucleophile can either attack this carbon or it can attack that carbon. In this case, those carbon are exactly the same. So it can attack either one. But then there is a situation where the carbon atoms are not the same. And so we'll see, we'll look at that in the future, which carbon will be attacked. Another thing, there's no carbocation rearrangement here because you are not forming a carbocation. If you are not forming a carbocation, then there is no rearrangement. Does that make sense? Our intermediate is a bromonium ion, so no rearrangement. Same thing like hydroboration. No rearrangement because we don't form any carbocation. Another thing is that you can only add bromine and chlorine whenever you're doing this reaction. Adding iodine will not be favorable because the product, the resulting product will not be stable. Okay, so this product is unstable. Remember the principle of reaction. Substances react together because they want to form something more stable. Does that make sense? At least more stable thermodynamically. So because the product of with the iodination will be unstable, then chances are that the reaction will not take place. Okay. Are we good up to this point? Reaction number 5. Oh God. There's a lot of reactions to remember. You know what? You need to make flashcards. But if you study the mechanism, trust me, you will not need the flashcards. If you study the mechanism, you will not need the flashcards. I think I have some flashcards. All you need to do is just to print them. I will look for them and give it to you guys. I'll post it on Blackboard. Reaction number 5, formation of halohydrine. Formation of halohydrine is very similar to what we did before. Okay, take note of the difference. In the first reaction, we didn't use water. We used methylene chloride. Okay, but then when you use water now, everything changes. Remember, water is a nucleophile because of the lone pair of electrons. Okay, and so when you use water, instead of adding 2 bromine atoms onto the double bond, you will add 1 bromine atom and 1 OH. Does that make sense? Because of the presence of water, that will lead to the addition of 1 bromine and 1 OH instead of adding 2 bromines. Is that okay? And so those are the products that will be formed. And in this case, we have 2 products. A major product with the OH over here, and then the minor product when you are adding 2 bromine. But technically, I don't even like it. Forget about it. The minor product doesn't exist. Okay, you're only adding that OH there. Does that make sense? Same thing with the chlorination. When you have chlorine and water present, one of the atom, one of the carbon gets the OH, and the other one will take the chlorine. I will say forget about a minor product. I don't like it. It will not be formed. It will not be formed. Now, let's look at the major product. I want you guys to observe the major product as a good chemist. Let's look at the first one. The first thing is that the double bond is not symmetrical. What I mean by the double bond is not symmetrical is that if you look at this double bond here, the carbon forming the double bond. One of them is having 1 hydrogen, and the other one is having 2 hydrogen. That's what I mean that they are not symmetrical. If they have the same number of hydrogen, I would say they are symmetrical. Because they have a different number of hydrogen, they are not symmetrical. So when you look at that, and you look at the product, what can you tell me? Look at that and look at the product. Where does the OH add up? Where do you add the OH? You add the OH on the carbon with fewer hydrogen. Does that make sense? The OH is added onto the carbon with fewer hydrogen. That is the mechanical rule. Okay, that's the mechanical rule. So you add the bromine over here and you add the OH over there. So the OH will add on the carbon with fewer hydrogens. Or the OH adds up to the more substituted carbon. Those are the little things I want you guys to know. Is that okay? It's the same thing with this one. If you do a comparison with that one, if you compare this carbon, if you compare that carbon and this carbon over here, you will notice that they are not symmetrical. One is more substituted than the other. Okay? And so the OH ends up on the more substituted carbon and the chlorine on the less substituted carbon. Does that make sense? It's important. It's very important. It's very important. And so in the mechanism, the first step of the mechanism is familiar. You form your bromonium ion. That's the bromonium ion formation. Okay? That's the first step of the mechanism, bromonium ion formation. Then I will zoom it here. Once we form the bromonium ion, the next step is our nucleophile. Remember I told you water is a nucleophile. So you take the water, and again, I don't want you guys to forget, whenever I say water, everything I say for water is valid for an alcohol. Does that make sense? Everything I say for water is valid for an alcohol. Because I told you in this class that water is a form of alcohol in chemistry. If you drink too much water, you will get drunk. Does that make sense? So water is a form of alcohol. That's what I want you guys to take note. Henceforth, look, this is how you write the structure for water. Let's see, look. This is water, right? And then this is an alcohol. Do you see that? So water is an alcohol in which the R is replaced by an H. So everything in this class that I say water, also know that is valid for the alcohol. Does that make sense? Yeah. So your water molecule is a nucleophile. The water molecule will attack this carbon, which is the more substituted carbon. So it will not attack this one. It attacks the more substituted. And then opens up the ring. That's how you end up with this product. And then take note of the positive charge on the oxygen. Because the water here, the oxygen already has 2 bonds. When it comes, it creates a 3rd bond. So that's why the positive charge is now on oxygen. Does that make sense? And so now you can have the deprotonation step, which is very familiar to all the other steps. And so you now have a deprotonation step, and you have your final product. Are we good? Yes. This guy here, we don't care about him. He can, okay, that's a good question. We don't really care about it, but technically the bromine now can react with this one, with that H2 to form HBr, which is an acid. So we don't really, that's why H3O plus is also an acid. So if the bromine minus react with that one, it will give you HBr plus water. So which is not really our center of interest. Does that make sense? Are we good with this one? So this, I want you guys to remember the mechanism. So why does the water attach to the more substituted carbon? Why does the water attaches to the more substituted carbon? Simply because when it connects at the transition state, when it connects to the more substituted carbon, it stabilizes the transition state. Remember, when the transition state is stabilized, the reaction goes faster. Compared to substituting it on the less substituted carbon, the transition state is destabilized and the reaction takes time to go. Does that make sense? So everything has to do with the stability of the transition state. The transition state is stabilized when it substitutes, when it connects to the more substituted carbon. And so you can have more reactions. You can have more reaction of that nature. Remember I said water is a form of alcohol. So this is an alcohol over here. Okay? And so the alcohol will add up to the carbon that is more substituted, and then the chlorine will add up to the other one. You can practice the mechanism. Use this one to practice your mechanism at home before you sleep. I will send you an email. I will send an announcement tonight at midnight to remind you to do the mechanism. I will do it. I will send an announcement tonight to remind you guys. Do your mechanism before you sleep. Yes, I will send an announcement tonight. Same thing with this one. In this case, we are reacting with HCl. Okay? Sodium chloride. In sodium chloride, the chloride ion is present in abundance. That's why one of the carbon gets the bromine, the other one gets the chloride. Does that make sense? That's hydrogen chloride. So it's the same reaction, follows the same mechanism. So I want you guys to try that. I will remind you today at midnight. Reaction number 6. Yes, there are a lot of them. There are a whole lot of them. Reaction number 6. Addition of a peroxy acid. Okay. The addition of a peroxy acid leads to the formation of two products. So, if we have our alkane, and we react the alkane with a peroxy acid, take note, you see the difference between this and a carboxylic acid? We have 3 oxygens. That's the difference. So we call those per-acids or peroxy acids. So when you react an alkane with a peroxy acid, you principally form 2 products. Okay? You form an epoxide, which is a 3-member ring molecule containing oxygen. We call this an epoxide. You form the epoxide and then you form your carboxylic acid. This carboxylic acid comes from the peroxy acid. So this is not our product of interest. Our product of interest is the epoxide. Okay? So whenever an alkene reacts with the peroxy acid, the product will be an epoxide. So if I have this carboxylic, if I have this alkane, that reacts with a peroxy acid, one of them will be called MCPBA. That's abbreviation for a certain peroxy acid. You will see the structure very soon. Okay, I will show you the structure. So if you react that with MCPBA, which is a peroxy acid, your final product would simply be this. That's an epoxide. Okay, that's an epoxide. So that's what a peroxy acid is. That's the structure of a peroxy acid. And one of the peroxy acid that you guys should familiarize yourself with is MCPBA. That's what is mostly used in the lab. Yes. So MCPBA is an example of a peroxy acid. So if you react this with MCPBA, that will be the product. Gracias, Garcia. Are we good? So MCPBA. I don't want you guys to worry about the mechanism of epoxidation. All I want from you is to know that when an alkene reacts with a peroxy acid like MCPBA, you form an epoxide. That's all I want you guys to remember. The mechanism, those I will meet in 407. We'll do it together. Okay, my 407 people, I know them. They're in this class. We'll do it together. Reaction number 7. Oh, God. Huh? Huh? This is number 7, right? Oh, 407, intermediate chemistry, organic chemistry. Yes, all chemistry majors are taking it. Yeah, we'll all do it, right, Zuri? We'll be together. So you can take it. And it's also a nice elective for those who want to take it. By the way, there will be biochemistry this summer. They will offer biochemistry 1 this summer. Yes, biochemistry 303. I'll be teaching that in the summer. But it will be super fast. Take note. It's a 5-week course, so it will be accelerated. Okay, let's continue. Reaction number 7 is called ozonolysis. Okay, ozonolysis. So ozone, this is from the ozone, right? The ozone, you know, O3. Like we say, ozone layer is being depleted. And then this lysis here simply means breaking. That's what lysing means. Okay. So ozonolysis means we are using ozone to break. So in this case, when we have our double bond, I will react that with ozone, which is technically O3 in the presence of zinc. If you react this with ozone, what you're simply doing is that you are dividing that double bond into 2. You are breaking the double bond into 2 and you are capping each end of the double bond with an oxygen. I want you guys to take note of that. That's our reaction number 7. So if we have our double bond and we react the double bond with ozone, okay, the product, you simply delete. You break that double bond into 2. So you break the double bond into 2 this way, and on each end of the double bond, we simply add oxygen. And so we are forming carbonyls. You could either form an aldehyde or you could form a ketone when you perform an ozonolysis. Does that make sense? When you perform an ozonolysis, you form a ketone. And again, I don't need you guys to know the mechanism for this one. The only mechanism I want you guys to know is the acid catalyzed mechanism and the bromination. Okay, the two types of bromination we saw, HBr and Br2. Those are the 3 mechanisms I want you guys to remember. The rest, you need to know the formation of their products. Okay, so for the ozonolysis, again, it's easy, trust me. By then your brain will be open. Don't worry. So ozonolysis, like I said, will lead to the formation of a ketone or an aldehyde, depending on what kind of alkene you have. Okay. So for example, let's look at this thing in detail. These are the conditions. Those are the reagents for ozonolysis. So whenever you see this, ozone at a very low temperature in the presence of the sulfide, then you should know that you're about to do an ozonolysis reaction. And in the ozonolysis reaction, you are simply breaking this double bond into 2. You are slicing the double bond. One end of the double bond, you cut them with the oxygen. And so this product will be an aldehyde because you have a carbon double bond oxygen with a hydrogen. That is an aldehyde. And the other end ends up being a ketone because the carbonyl is surrounded by 2 carbons. Does that make sense? So it depends on what you start off with. In this other case, we are starting with this other alkene here. And so the 2 products that are being formed are all ketones. All you do is break the double bond into 2 and then cap them with oxygen. And so you end up having ketones. Does that make sense? So everything simply depends on what you are starting with. I divide that, then I add the oxygens. That's ozonolysis. Same story here. This ozonolysis leads to the formation of 2 aldehydes. Because when I break this double bond and I cap them, I will form this and I will form that. Remember the difference between the aldehyde and the ketone. Okay, the ketone is a carbonyl with 2 carbons next to it, An aldehyde is a carbonyl with one hydrogen and one carbon. Does that make sense? Now, in addition to ozonolysis, I want you guys to be able to look at the product of ozonolysis and guess what alkene was used to make that ozonolysis, to perform the ozonolysis reaction. We usually refer to that as a retrosynthesis, okay? And so, if I give you these two products and I ask you, guess the alkene from which these products are obtained, all you simply need to do is delete the oxygen and combine them together. Does that make sense? So this is basically the reverse. That's the reverse of what we did in ozonolysis. And here we are representing that with a double backward arrow. I don't know. This is called retrosynthesis. So you're thinking backward. Okay? You're thinking backward because if you break this, then it gives you this. And then if you combine this, it gives you that. Does that make sense? I have 10 minutes left. I will not continue this one. No, but we'll do some problem. Trust me. Retrosynthesis. I will not do the other one. We are almost, I would basically say we have finished chapter 6 because we've studied all the reactions that we're supposed to study in chapter 6. It's true we haven't done oxidation with potassium permanganate. No, there's about 2 more reactions remaining. But we'll look at it later on. There are 2 more reactions remaining. But we've almost done all the reactions that are there. So everything you need now is to practice. The next thing we'll be looking at in this chapter will be the stereochemistry of the product. Are we going to have racemic mixture? Would that give us enantiomers? Would that be a syn addition or an anti-addition? Those are the things that we'll talk about on Thursday to wrap up this chapter and start chapter 9. Okay? But then my class is not finished. You remember, I will not leave you guys go like that. I will. Yes. Nope. Yes. No, summer only. Not during the school year. During the school year, I have another business, organic chemistry. So, problem number 7 from your textbook. What is a major product obtained from the addition of HBr to each of the following compound? We'll do number C. I will do number C. What are letter C? Oh, God. So that is C, and then we are asked to add HBr. So we are adding HBr. We know that one of the carbon we have H and the other one we have Br. Then you need to know which one. The one that is more substituted, we have the Br, and the less substituted, we have the H. And so if you follow that rule, which is the Markovnikov rule, the Br will be here. So that will be your product for number C. Go and do the rest. That's problem number 7 from your textbook. Okay? Go over, please. Go over and finish it. And you can finish it by doing the mechanism, although the question didn't ask for the mechanism. Because by doing the mechanism, you are practicing it, okay? You are practicing. I will keep emphasizing. I will keep emphasizing. There are other problems from this textbook that I like, not this one. Yes. B to problem C. What was the question?
When we have things like HBr, for example, we only have to show the bromine part of it or like the other part of it. We don't have to show
Well, if you want to show the hydrogen, that's fine.
Okay.
Yeah.
I just didn't know, like, on the test I saw.
No. If you want to show, that's fine. There's no problem. There's nothing wrong with showing it.
But then also, like, when we have like a methyl shift or a hydrogen shift, do we have to denote where it's got like the 1,2 or 1,3?
Yeah.
Okay.
Yeah. Problem number 14. Problem number 14 from your textbook says, I cannot zoom it further than this, okay? It says, how could the following compound be prepared using an alkene as one of the starting material? How could the following compounds be prepared using an alkene? Using an alkene as a starting material, okay? So I will do problem 14a. I will do problem 14a. So how can we prepare problem 14a? So one thing you need to note is that in this case, we are adding an OH. And so you start thinking, what are the different ways in which I can add an OH on a molecule? And we've talked about two methods. You can do hydroboration or you can do acid catalyzed reaction. Does that make sense? And in each case, you are adding an OH and you are adding an H. So the next H will be here. So these are the two groups that you've added. And so if you remove those groups, then that will give you the alkene. So the alkene from which that compound can be formed will be that. So if I remove this OH and I remove that H, I will create a double bond over there. And so this will give me my alkene. And that is not enough. Once you give me this alkene, you tell me that it will react with this alkene in the presence of water and an acid. That's what I want to see. So you give me the alkene and you give me the reaction condition. Does that make sense? You say, okay, I will use this alkene and I will use this reaction condition to form that product. Yes. You could also, instead of using that hydrogen, you could use this hydrogen. And if you use a hydrogen, then it will be that one, which is still the same. Does that make sense? Which is still the same. Problem number D, or what is it, 14D. I'm skipping some of them because I want you guys to go and do them on your own. If you don't do them on your own, you will not know it, because when I do it, it seems easy. It is not. It is not. And I will get the same problems from the textbook to give you in the exam. I will get them from here and give you back in the exam. So if you did it, you will be fine. If you didn't, you will have your eyes to cry, right? Yes. So in this case, we are adding an OCH3. We are adding the OCH3. So that's the addition of an alcohol under acid catalyzed condition. And so we need to be able to form the alkene. So it will add an OH, it will add an OCH3 and an H. So the adjacent carbon will have an H. So this is my adjacent carbon, that's my adjacent carbon, that's my adjacent carbon. So you could choose any of those adjacent carbon to remove the H. Does that make sense? You could choose any of those. So I will do this. Yeah, I still have 3 minutes. So let's call this adjacent carbon number 1, adjacent carbon number 2, and let's call that adjacent carbon number 3. You could choose any of those ones to remove the H. And if you remove the H, then you create the double bond. Does that make sense? So for the first one, let's do adjacent carbon number 1. If you remove adjacent carbon number 1, you will create a double bond over there, because you are removing this hydrogen. So that will create a double bond there. If you decide to remove adjacent carbon number 2, you will have that as a double bond. Does that make sense? If you decide to remove adjacent carbon number 3, or hydrogen, sorry. If you decide to remove the hydrogen of adjacent carbon number 3, that's what you will have. So these are the possible alkenes from which that compound could be made. And the reaction condition is you will need an alcohol in the presence of an acid to do that. Yes?
When you leave the hydrogen alone, what is the other, like when you take the oxygen away, are you taking the oxygen and the CH3?
Yeah, you're removing the OCH3 and 1 hydrogen. You're removing the OCH3 and 1 hydrogen. So the question now, between these ones, 1, 2, 3, which one is the best to use? Which one is the best to use? 1, 2, or 3? The first thing you need to notice that 1 and 3 are the same. Okay? That's the first thing. So 1 and 3 are the same. So let's reduce our choices between 1 and 2. Which one will be the best to do this reaction? Just vote. It's a vote. Just like what is happening in New Hampshire today. Right? So which one will be the best? I think 2 will be the best. 2 will be the best. Because 2 is the less stable of the alkene. Does that make sense? You are comparing 1 and 2. I'm repeating. You know, the one we say in the last minute of the class is always important. 1 and 2. 2 will be the best to use because it is the less stable. Remember we said for reaction to go faster, the reactant needs to be less stable. And so if you choose a less stable reactant, you expect it to react faster than a more stable reactant. And this is more stable because it is more substituted. This is less stable. This will give you a tertiary and a primary as intermediate. Whereas this will give you a tertiary and a secondary as intermediate. You see, if you're comparing 3 and 1, it's way better than comparing 3 and 2 in terms of intermediate. Does that make sense? Go and finish the remaining problem. There is problem number 14, 15, 16, 17, 18, up to 100. Do them.
What are the recommendation letters the university